My research shows that there is an imperative for restorative on-site remediation. Lead-contaminated soil poses a significant threat to communities, and I argue that this crisis is perpetuated by a fundamentally flawed system of hazardous waste management. My research question, What are the benefits and barriers to on-site remediation, evaluates that while on-site biological remediation methods offer a powerful, permanent technical solution, that the greatest barriers to implementation are not scientific but rooted in economic, regulatory, and ethical systems. To prove the technical viability, my process involved an analysis of various biological remediation techniques. I focused on phytoremediation, which uses plants, and mycoremediation and phosphorus solubilizing bacteria, which uses fungi and bacteria to immobilize, degrade, or remove lead contaminants. Phytoremediation and mycoremediation are proven, sustainable, and capable of returning the land to a usable state, such as for agricultural or public use, which excavation and disposal does not do. Mycoremediation represents a restorative approach to toxic heavy metal cleanup. Mycelium, the vegetative structure of the fungus, forms beneficial networks within the soil capable of both bioaccumulation and biotransformation of contaminants. Fungi secrete powerful extracellular enzymes to decompose organic matter. While known for degrading organic pollutants, these enzymes also alter metal compounds, increasing stabilization or binding them to organic complexes within the soil. Fungi Essentially, not only do the fungi bioaccumulate, sequester, remove lead, and immobilize lead from soil, they also improve the overall soil tilth. Mycological remediation has achieved success in social and ecological restoration. To track the process of improved ecological function, the following slides expand on soil health parameters. Measurable soil health parameters include horizonization, organic matter percent, water soluble aggregates, percolation rate, and bulk density. Additionally, micropore and macropore size, texture, composition, moisture content, and pedology. pH, base saturation, and cation exchange capacity. Soil organic carbon, color, classification, microbial biomass, bedrock parent material, and previous land uses. The mechanism of biomineralization, the PSB, work by converting soluble lead into a highly stable inert material called lead apatite. This process permanently locks the lead into the soil structure, preventing it from leaching into groundwater or being taken up through human ingestion. This provides a true, permanent, and on-site solution. Conventional abatement methods and environmental injustice. This method, excavation and disposal, operates by externalizing costs. It removes contaminated soils from places like California and exports them to states with less stringent regulations, perpetuating a cycle of displacement. Dissolved lead can quickly leach into the water table, creating an exponential public health threat. This instability proves that methods fail to provide permanent risk mitigation. Only on-site stabilization can immobilize lead permanently. Chemical fixation significantly increases the soil's bulk density and reduces the percolation rate, resulting in soil that is essentially concrete. The lack of ecological function makes it impossible to achieve true site restoration, and the chemical bonds can break down over time, risking remobilization of lead. Case studies in structural injustice. In a case study very near and dear to my heart, there was a lead smelter, ASARCO, in Smeltertown in El Paso, Texas, historically. For decades, this community lived with extreme lead exposure from the smelter's fallout. Even after the demolition, the lead contamination, the displaced soil, and the residual lead requires a permanent restorative solution. This site proves that displacement is not remediation. In 1975, the pivotal epidemiological study by Landrigan established a definitive, irrefutable link between the smelter's emissions and the alarmingly elevated lead absorption in children. Another case study, Exide Technologies from Vernon, California. This site resulted in a massive, costly cleanup effort involving thousands of surrounding homes contaminated by airborne lead dust. The scale of remediation highlights the devastating public health cost when contamination is allowed to spread, further proving that preventative, restorative on-site stabilization is exponentially cheaper and more ethical than cleaning up an entire urban area after the fact. The sentiment expressed by advocates that the cleanup plan leaves many to fend for themselves captures the profound breach of trust and the feeling of abandonment by the system. Barriers to a just transition. True success must be measured by the achievement of ecological function and restoration. This ensures that the soil is not just cleaned, but actually healthy and usable for future generations. Current policy inherently supports the flawed economic model by prioritizing speed and cost minimization, which favors excavation and disposal. Regulations must be changed to internalize the true social cost of disposal, making restorative on site methods the financially mandated choice. Disposal remains artificially cheaper than long term restorative biological treatment because costs are continuously externalized. Public perception, there is often a strong stakeholder preference for the immediate visible action of excavation and disposal over the slower, science intensive, but ultimately superior processes of biological soil restoration. We must integrate environmental justice advocacy and policy enforcement into traditional engineering mandates, demanding that regulators and legislators create a financial framework that makes restorative on site remediation the cheapest and most mandated choice. My methodology involved a comparative technical evaluation of remediation strategies. This process was designed to rigorously assess emerging on site biological alternatives against the standard traditional methods. The critical difference in my methodology was defining success. I moved beyond simple regulatory compliance to focus on restorative outcomes. My evaluation was thus based entirely on achieving measurable improvements across the three restorative metrics. My research proves that biological methods deliver a permanent solution by not only stabilizing lead, but by actively regenerating the soil itself. The data confirms this. We see measurable increases in water stable aggregates, improved percolation rates, and reduced bulk density. These outcomes ensure the land is safe, healthy, and usable for the community, fulfilling the demands of true environmental justice. The path to a just outcome. My research confirms that we have the permanent technical solution in on site biological remediation. The next step requires translating this science into mandatory policy. We must demand that regulators internalize the true social cost of disposal, making restorative on site solutions the new economically and ethically mandated standard. When we assess the full life cycle, traditional excavation and disposal methods are environmentally devastating. The hidden costs of excavation are precisely what exposed the flawed economic model. The initial price tag ignores several massive liabilities. First are the environmental costs, specifically the immense CO2 emissions and energy consumption from hauling contaminated soil hundreds of miles. Second, and critically, are the ethical and financial liabilities of displacing this contamination. By forcing this burden onto another community, they are perpetuating the cycle of injustice and fail to remove the long term environmental liability for the contamination itself. These externalized costs make the restoration of on site biological remediation methods the only ethical and truly cost effective solution. Biological remediation eliminates the immense long term liabilities associated with landfilling and the perpetual monitoring required by regulators. It dramatically reduces the CO2 emissions and the transportation costs, and most importantly, it restores the value of the land itself. Investing in ecological restoration today is exponentially cheaper than paying the social and environmental price of displacement for tomorrow. This table provides an essential comparative analysis of the three core methods, comparing excavation and disposal against phytoremediation, the biostabilization with PSB, and mycological remediation. Thank you for listening to my capstone presentation, and thank you for allowing me the opportunity to share my research with you.